All right, let's just jump right into this explainer and look at the invisible, frankly amazing forces holding literally our entire universe together. Apart from the noble gases, practically no element is just chilling out there as a solitary atom. Everything you touch, see, breathe, it's all built from these atomic clusters. But what actually drives them to link up in the first place? What does the architecture of this microscopic world really look like? Seriously, why do they bother forming molecules at all? Well, picture atoms as these incredibly restless little entities. On their own, they're inherently unstable, and they are desperately trying to lower their energy. Their ultimate goal in life? To reach that perfectly balanced, low-energy Zen state of a noble gas. So when two atoms get close, you get this chaotic mix of attractions and repulsions. If the net result is an attraction, boom, the potential energy drops, and a chemical bond is officially born. So to see how they pull this off, here's our roadmap for this explainer. 1. The quest for stability. 2. Types of chemical bonds. 3. Breaking the octet rule. 4. Valence bond theory. And 5. The magic of hybridization. Let's get to it. Number 1. The quest for stability. Okay, so the fundamental driving force here is that relentless hunt for minimum energy. And to get there, atoms use a very specific currency called valency. The word actually comes from the Latin valentia, which literally means combining capacity. It basically tells us exactly how many electrons an atom needs to lose, gain, or share to hit that magic number of 8, the Lewis octet. Having 8 electrons in that outermost shell, that is the ultimate VIP status of those ultra-stable noble gases. Moving on to 2 types of chemical bonds. Right, so atoms have a few different strategies to negotiate these electron trades. First up is the ionic bond. This happens between totally dissimilar atoms. It's a complete no-take-backs transaction, where one atom dumps its electrons and another swoops in to grab them. Suddenly, you've got these oppositely charged ions locked together by a massive electrostatic attraction. And since that force radiates everywhere, 360 degrees, they don't just form cute little pairs. They build massive 3D crystalline lattices. Think about the table salt in your kitchen. Because they're locked in so incredibly tight, they have sky-high melting points, and, fun fact, they only conduct electricity if you melt them down or dissolve them. Now contrast that with covalent bonds. If ionic bonds are a straight-up purchase, covalent bonds are more like a cooperative roommate agreement. Instead of handing over electrons, atoms with similar electronegativities mutually share pairs of electrons to finish off their octets. The bond between the actual atoms is super strong, but the forces between the resulting molecules, those van der Waals forces, are actually pretty weak. That's why covalent compounds are usually soft solids, liquids, or gases, and generally terrible at conducting electricity. But here is the absolute game changer. Covalent bonds are rigid and highly directional. This 3D geometry is what allows for isomerism, where you can take the exact same building blocks, arrange them differently, and end up with completely distinct substances. All right, section 3, breaking the octet rule. Because honestly, just when you think you've got the rules nailed down, everyone wants exactly 8 electrons, nature throws a massive curveball. Look at the central boron atom in boron trifluoride. It starts with 3 valence electrons, shares 1 with each fluorine, and, well, that only brings its total up to 6, not 8, 6. And yet it forms a totally stable molecule. It's perfectly happy with an incomplete octet, creating what chemists call an electron-deficient compound. So much for the rules, right? And then on the flip side, you have the hoarders. Take phosphorus pentachloride, PCl5. Phosphorus forms 5 single covalent bonds with 5 chlorines. That gives it 10 electrons in its outermost shell. 10! It pulls this off by expanding its octet right into its vacant, higher-energy d orbitals. And to explain this without totally trashing the octet rule, a chemist named Shugden proposed this idea of singlet linkages. It's a really cool theory that basically suggests some of these bonds are actually just weaker, single-electron bonds used specifically to maintain all that crowded stability. Which brings us to number 4. Valence bond theory. Since that basic octet rule clearly has its loopholes, valence bond theory steps in to explain what actually happens when these atomic orbitals physically smash into each other. There are 2 main ways this goes down. First is the sigma bond. This is a strong, head-on, axial collision packing a massive 80 kilocalories of bond energy, and it completely dictates the shape of the molecule. Pitted against that, you have the pi bond. This is a weaker, lateral, sideways overlap of electron clouds hovering above and below that main sigma bond. It essentially locks the atoms in place, restricts them from rotating freely, and this is key, it literally never exists on its own. It's always a sidekick to an existing sigma bond. Finally, section 5, the magic of hybridization. Okay, welcome to the true architectural wing of this explainer, Pauline's genius concept of hybridization. What happens when an atom's pure s and p orbitals just aren't cutting it for a specific bond? Well, it mixes them. It's literally like mixing red and white paint to get the perfect shade of pink. When you intermix one spherical s orbital with two dumbbell-shaped p orbitals, they morph into three brand new, identical sp2 hybrid orbitals. And because electrons naturally repel each other, these three push apart as far as geometrically possible, which gives us this perfectly flat trigonal planar shape with exact 120-degree angles. Now when things get a bit more wild and we drag d orbitals into the mix, like with our old friend phosphorus pentachloride, we get sp3 dehybridization. Now nature has to figure out how to arrange 5 hybrid orbitals in 3D space. It solves this spatial puzzle by creating a trigonal bipyramid. You get 3 orbitals sitting flat in the middle at 120 degrees and 2 pointing straight up and down at exactly 90 degrees. Every single atom positions itself perfectly to minimize that electron repulsion. And this whole thing culminates in these massive, frankly beautiful structures like sp3d3 hybridization, which we see in iodine heptafluoride. In this one, 1s, 3p, and 3d orbitals intermix to form 7 identical orbitals. 7. The resulting geometry is a crazy complex pentagonal bipyramid. 5 atoms form a precise flat pentagon around the center at 72-degree angles, with 2 more sitting straight above and below at 90 degrees. It is just an incredible, flawless display of 7 atoms orbiting a central point in absolute spatial harmony. So we've gone all the way from the basic currency of valence electrons to the incredibly intricate 3D geometry of molecular architecture. So right now, just take a second and look at the objects around you. The hard screen you're watching this explainer on, the fabric of the shirt you're wearing, the water in your glass. Ask yourself, how does this invisible microscopic drive for subatomic stability, these rigid covalent angles and giant ionic lattices, literally create the physical reality that we touch and experience every single day? It's pretty wild to think about. It's really all just atoms finding their perfect geometric balance.